David Ngobeni. You can see him here in the picture. I'm presenting his poster at one of the meetings. And he's the one that did most of the resistivity work. And the next slide. The work was completed at a small children's, sort of an orphanage called the Day Spring Children's Village. And this is a home to about 100 students and staff, what we would call at-risk students. They're not 100% orphans because they often still have one parent living, but that parent may be suffering from HIV or alcoholism, or may be in an abusive relationship. So the students sometimes fall through the cracks because there isn't any programs to deal with this sort of thing. So they come to the school, and at least during the school year, they're housed at the school, and they're out of this often terrible environment that they face at home. And Dayspring now has their own Facebook page, so if you're interested in following up on them, you can just do a Dayspring Children's Village on Facebook, and it'll go straight to their page. And this is just some of the kids that are there at the program. Next slide, please. My goal with this was to pick a place where I could get to it easily. I mean, the problem in Africa is there's about 1 billion places we could all put our time and effort into. And so I wanted something that I knew I would be able to get to reasonably easily and to involve a number of our graduate students in. So the Dayspring Children's Village is not that far from Johannesburg, as you can see on the map. It's about an hour-and-a-half drive away. And there's some small, modest accommodation nearby, so that we were able to rent a small farmhouse nearby, so that we didn't have to strain the school's resources when we actually went there and did work. If you go to the next slide, you'll see it's located fairly close to some major roads, and it's not that hard to get to. Like I said, it's about an hour-and-a-half drive to the northwest of Johannesburg. And next slide. And our objectives were really to, first of all, try to determine the effect of alien trees on groundwater. There's a big program in South Africa called Working for Water, which is looking at the effect of invasive alien tree species on surface water. So, for example, they have cleared out several riverbeds of these invasive blue gum trees, these eucalyptus trees from Australia, and lo and behold, the surface water has come back. Streams that haven't run in 30 years are now having water on the surface. So we thought we could examine this at the Dayspring School because they have a very large stand of these blue gum trees, and we think it may be affecting the groundwater also. So we thought we could use geophysics to try to test that idea. In addition, we want to provide a better geologic and hydrological insight into that area. It's a fairly complicated area, but it seems to have fairly extensive groundwater resources, but it's been poorly studied. And finally, we want to locate a well for clean water for the school itself, and especially to train students, our geophysics students, in practical and novel applications of geophysics. So if we go on to the next slide. The regional geology is fairly simple, but as you can see by the dashed lines on the map there, it's actually not very well mapped. So I've put the location of the Dayspring School there, and that dark black line on the western side of the school boundary is a syenite dike. To the north of that is the green diabase or dolerite sills, which actually turn out to be pyroxenites, which we just, when we looked at thin sections. And finally, the rest are slates and hornfells that are fairly old and metamorphosed. So the rocks themselves are not hosting an aquifer. It's actually at the contact between the sills and the metamorphosed sedimentary rocks, the shales and hornfells, that seems to be hosting the aquifer. Next slide, please. The plot itself is actually fairly small. It's about 300 meters by 400 meters. And it used to be an old game farm, so it was kind of a place where people would bring their buddies and hang out for the weekend and you know, host a few big family events at. And then it was turned into the school eventually, and you know, hosting disadvantaged children. And 30 years ago, they used to have extremely good groundwater. And in fact, you can see around the school, which is outlined in the white boundary, you can see around the school there's actually orchards, and those are peach trees. This area is world famous, well, at least in South Africa, for the Maharand peaches that come from the area. Unfortunately, you can also see, probably in one of the subsequent photos, the peach trees are also all dying. So the groundwater is becoming less and less, although there's some disputes about property in the area. Some people have run off with each other's partners, so there's some disputes about the orchards, and they're all falling into disrepair. And in 2007 and 6, the DS1 borehole there is the main source of water. And that one actually dried up about 3 years in a row. And the school had to close down and send everyone home simply because there was no water. And so at some point in 2007, they managed to raise enough money to drill another borehole, and they just drilled and drilled and drilled until they hit water. And that was borehole DS2 at 162 meters deep. That's extremely deep for a water borehole. The other boreholes that you see there, DS 3, 4, 5, and 7, 6 and 7, are old boreholes back from the time when this was a game farm, and they are all defunct. None of them have water, although DS7 appears to have water at depth. When you pump it, it dries out quite quickly. So the two boreholes that have water are in blue, and DS1 is a depth of about 50 meters, and DS2 at 162 meters. You can also see along the eastern boundary, there's a large stand of trees. These are these blue gum trees and yellow wattle trees, which have been shown to consume about 200 meters per tree per day of water. So we think they may be dramatically affecting the groundwater in the area. Of course, it's not an easy site to work on. We've got power lines. That big red stripe on the western side is a major power line, so that gives us complications for some of the geophysics. We also have a gas line running right through the property, and then the cyanide dike, which is shown in yellow off to the west. Okay, next slide, please. Okay, this shows what the area looked like previously. This is a historical photograph on the left-hand side of that they actually had on site, and you can see how the land use has changed and how all the peach trees, this is about 50 years ago, this photo, and how all the peach trees have been planted and grown up, and now they're actually dying off, and how the land use and also all the other trees in the area have grown up. Okay, next slide, please. If we look in detail at the site itself, we set out a grid with our differential GPS. This is obviously just in the computer, but we use these points. And we have no outcrop. There's absolutely no fresh outcrop on the site itself, but we are able to map the float. So what the students did was to wander around and pick up whatever pieces of rock they found on surface and map out the different rock types. So for example, the pyroxenites are shown in red. These are what we called earlier the sills. The hornfells, or the sedimentary rocks, the metamorphosed sedimentary rocks, are shown in green. And the cyanide dike is shown in purple. And it appears that there's possibly a finger of the cyanide dike coming onto the property, although we could find no more evidence of it except for tiny little pieces of float rock on the surface. Okay, next slide. Next slide. So this just shows a couple of the participants. These are some of the kids from the school on the left, and then David showing off some of his rocks and some of his fellow students. And next slide. One of the fortunate things that happened is when they drilled borehole DS2, which went quite deep, they were able to save the chip samples. So although they weren't drilling core, at least the driller was smart enough and put little piles of the dirt all around the borehole in order so that we were able to sample that and figure out an approximate stratigraphy of the borehole going down. And we that at about 55 meters depth and at about 75 meters depth, the drilling actually ran into some incredibly hard rocks. These were so hard that when the material comes up, it comes up as dust. So it's actually, we're not quite sure what it is. It looks like it's one of these sills, these bushveld sills that has come through. So they're quite isolated. It basically isolates these two different aquifers from each other. Unfortunately, for about 30 meters towards the bottom of the borehole, there were no samples taken. Okay, next slide. This is Naraka Devkuran, who was one of our honor students who's now working for Anglo-American. And early on in this project, we really didn't have a lot of equipment. So we essentially just decided to do it anyways and figure out and use what we could. And you can see here we're using an old dumpy level, which provided pretty good results for the gravity survey, the original gravity survey that we did. But it is quite time consuming. Next slide, please. And as we moved along, we got some more equipment and got more people involved, and we hired a hydrologist right towards the beginning of the project. And so he came out, he had a little bit of equipment, and we were able to measure the pH, the total dissolved solids, and the conductivity of the water. And we had a special analysis done. We were able to analyze for tritium at Ikemba Lab. And we're able to do this for free if we involve students. So that's one exciting thing about doing research here in South Africa. Everybody's always willing to help students at the national labs. So for example, we're able to use the nuclear reactor for research, for example, in neutron tomography, and also Ikemba Labs to do the types of analyses. So if we go to the next slide, we can see the results of the two boreholes that actually have water. So DS1 is the one that's up in the north west of the property. That is the shallow borehole, pumping depth of about 30 meters and extends down to 50. And it has reasonably good values. And it shows a small amount of tritium, which means it's being recharged. So the tritium is important because that means it's been exposed to the atmosphere at least since the nuclear age. The interesting thing is borehole DS2, which unfortunately has quite a high pH, and so it's not clear that this is particularly good for drinking water. But if you notice, the tritium is 0. This means this is quite old water. So it's very clear, just as we suspected from the borehole, that these two aquifers are very, very different. Okay, next slide, please. So the geophysics that we proceeded to do, we tried to do a whole bunch of different things, partly to train ourselves and our students, and also to solve the problems we had tasked ourselves with. The first project was to look at gravity in 4D. We wanted to see if we took our gravity measurements and then repeated them. We have a very bimodal weather system in this area of South Africa, where we have a 6-month-long rainy season and then a 6-month-long dry season. So we thought we would take a look at the change in the gravity, which would most likely just be due to water because the rocks aren't running around, and we would be able to measure how much water goes in and out of the system. And then we also wanted to look at magnetics and seismic refraction. We even had a little look at ground penetrating radar to try to map out the tree roots. And finally looking at time domain EM, and the most effective proves to be the DC resistivity. Okay, next slide. So one of our students was Sally Ann Lee, who is shown here with our differential GPS. And once we got going on the project, it was funny how equipment applications that had been pending for years suddenly started coming through. And so we were able to raise money for a full RTK differential GPS. And this means it is real kinematic GPS, so you can see the antenna there talking to it, and it gives you your position in real time. This is just an amazing instrument, and we're very lucky that the trees in the area are all quite low, so we had absolutely no trouble using this, and we got extremely good results. So if we go to the next slide, we'll see the trees didn't affect the readings. We did more than 10% repeats, partly because we were learning how to do everything and we wanted to make absolute sure of all of our data. So for any particular survey, we did more than 10% repeats on each survey, and they were all less than 2 centimeters discrepancy in Z. And then the repeats that were 6 months apart were all less than 5 centimeters in Z. And this is a pretty good result. If we can go to the next slide. We can see an example here of some of the data and many of the repeats we did. You'll see it's much more than 10%, largely because we're learning how to use the equipment and we're working with students and we're trying to emphasize best practice and how important repeat measurements are. So you can see very, very small differences in some of the readings, but overall excellent data. Next slide, please. We then were able to borrow a CG5 gravity meter, and subsequently we have been able to purchase our own CG5 gravity meter. These are very expensive by anybody's standards. They're about $90,000, so we're very excited to have our own. And we did a 20 by 20 meter grid over the whole area to try to compare at the end of the rainy season in April, and then again at the end of the dry season in the September-October time frame. And we didn't get perfect results, but we did pretty well. Part of it was students learning how to use the gravity meter and not realizing quite how finicky everything is. So this is an experiment we're actually going to repeat probably this year and into next year, simply because we want to try this out again. We're pretty happy with the results, but we've learned quite a bit doing it the first time. So if we go on to the next slide, we'll see the layout of the grid and the number of repeat measurements we did, and you can see some gaps in the data. That's where some of the buildings are. So this just gives you an idea of how many measurements we did and how many repeats. On to the next slide. And the results are pretty interesting. On the left-hand side, we have the Bouguer gravity, which essentially just maps out the different rock types and amount of soil cover. So in the northern part, you see that we have a very strong positive gravity signal, and this correlates well with the float that we saw on surface to those pyroxenitic rocks. So we think the pyroxenites are up in the northern part and extending to the eastern part. The soil cover, we'll discover when we look at the resistivity, is much thicker on the western side than it is on the eastern side. And we see perhaps a hint of something coming through from the south to the north that may actually be this cyanide dike. On the right-hand side is the difference between the two surveys. And there is a little bit of noise in this signal. The Bouguer map I show on the left is data that I myself collected, and I'm extremely careful and paranoid and super careful about it, so we had extremely good statistics on that. Unfortunately, the data the student collected was not quite so uptight about, so there is a little bit of striping in this difference data that you can see, partly due to that. So again, we want to repeat it, but if we go on to the next slide, I'll show you what the lines are. This is just to keep in mind where line number 7 is. That's over on the left-hand boundary, the western boundary. And line 15 is one in from the row of trees on the right-hand side. And if you go on to the next slide, you'll see on line 7, the difference, there's almost no difference whatsoever between the April and October surveys. They match extremely well. But if we go on to the next slide, we'll see on the difference between the October and the April survey, there's quite a significant difference for a large part. And that actually happens to be where the majority of the trees are. So we see the effect perhaps on the water from some of the trees. There's certainly more water in the system during the wet season than there is during the dry season, which are the dark blue dots. Okay, if we move on to the next slide. Okay, so the overall change in gravity, the biggest change that we saw was about 0.25 milligals after about 6 months. And this is certainly resolvable with the type of gravity survey we did. And now that we've got more experience with this, I think we'll get an even better result. The 4D shows that the most water variations are near the trees, so not a big surprise that the trees are taking quite a bit of water out of the system, but also variations at the pyroxenite and hornfels contact. This is that contact between the intrusive sills and the metamorphosed sedimentary rocks. Okay, next slide, please. Another honor student that did work on the project was Obone Sapato. He's just recently been hired by Anglo-American. He's finished his master's degree with me, and he's been seconded to the De Beers Corporation. So he's out there looking for diamonds. And we started his project with one of our old magnetometers, because that's all we had. And so you see here him working here and explaining what he's doing to some of the kids at the school. And next slide, please. And his results are quite interesting. You can see on the left-hand side are the results of the ground magnetics, and on the right side it says aeromagnetics. Now this was quite interesting. It turns out one of the other students was socializing at after one of our geophysical talks, and the CEO at the time of the local branch of FUBRA was listening to him, and he said, "So what are you working on, young man?" And David said, "Well, I'm doing this project at this orphanage," and he gave his 30-second elevator talk, and he did a very elegant job of it. And FUBRA said, "We can fly that for you if you would like us to." And so he said, "Yes, thank you very much." So I always tell this story to our students to let them know how important it is be able to articulate what their projects are about and to have the confidence to talk about them. So we actually have airborne magnetic and electromagnetic data over the site. And you can see something really funny on the ground magnetic data. There's that north-south linear feature going right through the center of the data. And at first we thought, wow, maybe we found the, maybe there's a dike running through here, and maybe that's what's responsible for the water at DS1. And unfortunately, you'll see when we get down to the resistivity results, it actually turned out to be a pipe. And the reason it looks so wide here is because we actually ran our magnetic lines in a north-south direction because we were looking for that contact in the northern part of the magnetic survey. So the ground magnetic interpretation and the aeromagnetic interpretation match reasonably well. and it matches reasonably well with the gravity interpretation too. If we go on to the next slide. And this shows Louise Pellerin and her husband Jeff, whose name I've forgotten his last name there quickly, and two of our students, D.P. de Villiers and Sally Ann Lee. It turns out we were able to also purchase a new magnetometer, and that's what's shown. DP is modeling that on the right-hand side. And this is a WalkMag, which is a incredible advance over the old magnetometer that we had, because it incorporates the GPS into the instrument itself. So you simply walk along and it takes measurements as you walk, and you can define how frequently it takes measurements. But the results are significantly easier to download and work with, and you can get what used to take several hours of post-processing after you collected your data is now extremely quick to collect. So we were using this to try to define where this anomaly was that we saw on the old ground magnetic data, and they have commenced to dig this pipe up to see if it's we think it's a pipe, and we think it actually may be contaminating the borehole number 2, DS2. Okay, on to the next slide. So the one piece of equipment that we actually purchased with the Geoscientists Without Borders money, which was really essential to doing this project, was the resistivity meter. We had an old system that you had to swap the electrodes around by hand, and it used to take us 4 days to do one profile of the same length, that it now takes us 4 hours with the new equipment. So we were extremely excited, but there were some delays getting the equipment, and my student had already started his project and he was sweating bullets about getting it. So the day it was delivered, here we're shown taking delivery of the equipment, we actually drove directly to the field. We never even brought the equipment into the building. We had the insurance and everything all set up, and we literally just transferred it from Terry, who was the dealer on the right, and put it in that truck on the left. And if we go to the next slide, we see a very excited David Ngobeni working with his new equipment. He actually had to sit down and figure it out in the field. Unfortunately, this particular day was cut short by rain. I had to tell him, please, you've got to protect the equipment and take it inside. But he was so determined to get it running. We got it out of the boxes and into the field and started collecting data on the very first day. So this equipment has turned out to be some of the most useful equipment we've had. You'll see the results here for the Dayspring Children's Village, but also we've been able to use it on our field school, which is also sponsored by the SEG, and on many, many, many other projects. We're doing currently an acid mine drainage project with it also that's looking at bioremediation of acid mine drainage. So this equipment has been absolutely fantastic, and we'd love to see it used even more. On to the next slide. So David had the idea for his MSc to actually use time-lapse resistivity. We had seen the results from the gravity looked pretty promising, so we wondered if we would see significant results with the resistivity. We also knew that the resistivity would help us map out the groundwater and the underlying structural features, because we had collected some data with the older system, although it was very tedious. So we looked at repeating data. So we can see here from 2009, 2010 with the old equipment. We saw some temporal variations, but we were very excited because the results were very repeatable. So we knew we were getting good results. With the new equipment, we were able to get a much longer spread, and then we bought 2 new cables also in 2012 to extend the depth of the survey even deeper. So if we go to the next slide, we'll see some of the results. If we look at on the right-hand side there, these were the first couple of lines of data that we collected with the old system, and you can see on the top it says August 2009, which is end of the dry season, and March 2010, which is the end of the rainy season. And you can see the data looks very, very similar, although there are significant differences. And we think the difference plot at the bottom is highlighting some of the fractures in the rocks underneath. There's definitely a weathered zone at the top that is holding more moisture, which isn't too surprising, down to about a depth of about 10 meters. And then the very corrugated rocks underneath that appear to be hosting fractures that water is going through. Next slide, please. So then David was able to set up the new equipment, and he got very, very ambitious. And you can see all of these lines he did, lines 7, 9, 11, 13, 15, and 17. And then on the side he did profiles 10, 12, 15, 17, and 19 labeled with the P's. So what you see there on the left-hand side are the profiles, well actually these are the lines, 17, 15, 13, and then line 11 looks a little funny, and then 9 and 7. It turns out line 11 is along that pipe. So you can see the effect of the pipe on the conductivity. It just completely screws up the interpretation of that. But you can also see as we move from line 17 in the east across the grid to line 7 in the west, the thickness of the soil cover increases dramatically. And we also noticed that on the gravity data earlier. Okay, next slide, please. The next slide shows the cross-cutting profiles. So these are profiles 10, 12, 15, 17, and 19. And unfortunately, they're in reverse order from what they are on the map. So you'll just have to swap them around in your head. But you can see each one of them cross-cuts that pipe. And you can see how unfortunately, the pipe is affecting the resistivity results at depth. But we can get a sense that the thickness of the weathered zone is increasing from west to east along this. Okay, and next slide. Okay, the next couple of slides are a 3D view on Google Earth of the results. Here we're looking down from the south to the north, essentially along that section of pipe. And you can see the soil cover in the west, or the soil and weathered rock zone in the west is much thicker than it is in the east where the trees are. And if we move on to the next slide, we're now looking towards the, we're looking towards the east, so from the west to the east, and we've just got a couple of those cross lines. And next slide, we're going to go through these next ones quite quickly. So next slide, and now we're just putting the next slide, we're putting the lines on as we progress from the east to the west. And the next slide, and that's on line number 11, and the next one, and the next one. Okay, and we can see how the thickness has increased as we go to the west. And one more slide to take out that nasty line 11. There we go. And we can really see the structure of some of the fractures that are coming through, and where the thicker zone is to the north of the grid, where actually the one borehole is that actually hosts the clean water. Okay, and next slide, please. Oh, here we zoom in a little bit more, and I think we zoom in one more time. Yeah, so that just gives you a good view of what the data looks like. Okay, and next slide. And I think one more. Okay, and that gives you kind of a cross-cutting view. And finally, David was able to put together kind of a 3D model of the resistivity results, which has allowed us to really think about where things are. There was a problem with the borehole DS2 because the water was coming out. It was actually quite smelly, and they thought it was contaminated. Some of the earlier testing they did on it suggested it was contaminated. And we think because that pipe actually goes right next to it, that pipe must be leaking and contaminating it in the very near surface. So one of the things they're doing right now is trying to dig that pipe up, at least around the area where the borehole is, so that it doesn't interfere with that. Because a borehole water at that depth in an anoxic environment really shouldn't be contaminated. So it's some kind of interaction with something near surface. Okay, and next slide, please. So our conclusions are that the top aquifer is largely associated with fractures, but is constrained to the top 50 meters. This is based on the boreholes. The time-lapse resistivity has helped us map out the fractures, and the time-lapse gravity shows significant differences, especially close to the trees. Because these trees are invasive, and there is a large program throughout the country to remove these invasive alien tree species, they have commenced to start cutting these trees down. But unfortunately, it's quite a slow process. We didn't quite realize the technical skill needed to get these big trees down. They're well over 20 meters tall, and unfortunately, they're right on the fence line. So this is taking a lot longer than we thought, although they're using the trees for firewood and starting a small firewood business to help fund that. The lower aquifer is old and isolated and possibly has some contamination from a pipe. So if we move on to the next slide. I just wanted to say thank you to everybody who's been involved. The students have been incredibly helpful, and the kids have been so much fun to work with. And next slide. And I'm very excited about the future of geophysics. These are some of the kids that were hanging around with us at the school and constantly asking us questions. And next slide. And this is one of the kids that was the daughter of one of the people that was visiting us from Penn State. So she got really excited about the seismology. And finally, the next slide is just to acknowledge the many different contributions from different programs, this university and Foodgrow and a whole bunch of other companies that have really contributed to this. And finally, to encourage everybody to get involved, if we go to the last slide, I think Rhonda made a very good plea earlier on to get involved with Geoscientists Without Borders or to donate, and I want to say thank you for listening to me. It's been a really fantastic project and been very inspiring for all of the students. Thank you.
Sue and I are in communication. If you have a question that you want to think of later, go ahead and ask it in an email, and I'll go ahead and forward that back and forth. And don't forget that our next webinar will be in July 16th at this point. And so watch for the notices, and if somebody is not on the invite list and they would like to participate, please let me know and I'll invite them to the next one. Thank you, Sue. You're wonderful as always.
Great. Thank you very much for listening.